Good morning, and welcome to this presentation on effective electromagnetics teaching no matter what. My name is Hugo Espinosa from the School of Engineering and Built Environment at Griffith University in Australia. I would like to acknowledge the co-author of this paper, Professor Levent Sevgi, from the Faculty of Engineering at Istanbul Okan University in Turkey. For the past years, the methods and delivery of learning and teaching have evolved significantly. The adoption of traditional face-to-face instructor-led teaching has diminished in favor of more contemporary pedagogical strategies encouraging active student participation. The rate at which these strategies have been adopted has accelerated since the beginning of the global pandemic in 2020. All educators, even those with prior experience in online teaching, had to rapidly adapt their teaching methods and develop sufficient resources to satisfy the unprecedented demand for purely online teaching. This sudden transition introduced novel complexities to the student learning process, exacerbating existing challenges in the methodology and practice of electromagnetics education. Despite the easing of COVID-19 restrictions in several institutions around the world, the delivery of learning and teaching has not completely reverted back to pre-COVID-19 practices. Rather, a greater degree of innovative blended learning strategies are being utilized. With a focus on electromagnetics education, some of the pedagogical strategies that, according to the literature, have successfully been employed in electromagnetics courses include project-based learning, HyFlex, flipped classroom, experiential learning, and competency-based learning. As the COVID restrictions ease around the world, these strategies can easily be implemented for a delivery online, in person, or hybrid. But no matter what approach is being employed, it is important that these strategies encourage active student participation, which aim to increase student skills, student engagement, enhance student learning outcomes, and improve knowledge retention. It is very important to provide engineering students with sufficient technical abilities and practical skills that are required in the industry. However, the wide variety of pedagogical techniques available for teaching and the different modes of course delivery have varying effects on student learning outcomes. Over the past 2 years, literature has focused on comparing the impact between online and face-to-face delivery modes and how this relates to student performance and learning outcomes. Results have been both positive and negative, but this is attributed not only to the learning model and delivery mode, but also to the context-specific factors unique to students and educators in different environments and geographic locations. Looking into more detail about those factors that relate to the environment and geographical location, but also to the variations in curricular content, access to resources, connectivity, instructor expertise, and infrastructure, I came across this paper published in 1990 in the IEEE Transactions on Education, where Professor Rosebaum conducted a survey with several countries around the world to gain some international perspective on the teaching of electromagnetics. These countries included Germany, Japan, India, Australia, Brazil, and China. The report concluded that challenges in teaching electromagnetics courses were comparable in several countries around the world, and that students' interest in electromagnetics is continuously declining. In his own words, Professor Rosebaum mentioned that, perhaps we are not inspirational enough as educators, perhaps there are better methods to accomplish our goals. In order to provide some common ground, participants were asked to consider several questions, including students' mathematical background, what methods of instruction were used, novel or innovative techniques used for content delivery, teaching aids, and students' attitude towards electromagnetics. The answers to those questions and the perspective that emerged from the responses were surprising. They showed that there was a decline in students' interest in electromagnetics. Students were looking for more immediate relevance and applications. That's why they would opt for other courses in their degree. Traditional teaching was predominant, and all participants agreed that after understanding the fundamental theory, applications and the use of existing software solutions should be enforced. Now, these are remarks and opinions for 30 years ago. The interesting thing is that the challenges in electromagnetics education continue to date. The literature presented here is mostly recent. Apart from my 2012 paper, all others are from 2 years ago. In here, authors raise questions and concerns about the different learning models, the effectiveness of the different delivery modes, the course content and structure, student performance and satisfaction, the perceived relevance of a subject by students to future employability, and even the experience and devotion of lecturers towards electromagnetics courses. This literature also identifies that the topics covered might be dictated by the regional needs of students and the interests of accreditation bodies and industry. Most importantly, there's a consensus that a balance should exist among the fundamental theory, computer simulations, and electromagnetics applications. Educators from this era also believe that an effective teacher must be passionate about their subject. In his paper, Electromagnetics Education, Its Future and Challenges, Professor Notaros states that there's great non-uniformity and challenges in terms of general questions such as more fundamentals versus more applications, more concepts versus more computation, more fields versus more waves, traditional lecturing versus active learning, face-to-face versus online, etc. Maybe it's time to consider the second version of the survey around the world. I'm actually intending to start the study, and everybody is welcome to participate and contribute to it. What is very important to consider is that no matter what learning model we use, or what delivery mode we employ, or what curricular content we include in our courses, or what assessment structure we adopt, or even what teaching philosophy we adopt, electromagnetics must be taught effectively. It is important to retain the fundamental features when teaching an electromagnetics course, regardless of how the course is actually delivered. The course should be founded under three well-balanced pillars, which are theoretical background, hands-on training and experimentation, and computational modeling. In the theoretical background, the correct use of mathematical tools such as vector calculus is essential, as it aids in the conceptual understanding of static and dynamic fields, charges, potentials, etc., all what leads into Maxwell's equations. Hands-on training involves active student experimentation and problem solving. Employers require engineering graduates with technical and practical attributes in addition to the fundamental knowledge. In electromagnetics courses, the practical experimentation could include realistic engineering applications. Simulation and visualization interactive tools have been developed in the past years as an effective learning method and teaching resource. Such tools aim to enhance the student understanding of the theoretical fundamentals and increase their engagement in the subject matter. As it can be seen, these pillars are interrelated. They are not cyclic, and they need to be balanced. This aligns well with the findings from the past years, which makes this paper a corroboration of what several educators have emphasized. The fundamental features that span the three pillars of theory, practice, and computational modeling include physical and mathematical relationships, active learning and experimentation, computational modeling and visualization, and speaking with numbers. As professional engineers, we speak with numbers. A number is given as a result of a measurement or a computation. The question is, what quantities can be measured or calculated? Basic quantities such as length, weight, time, voltage, current, stress, temperature, electric and magnetic fields, etc. can be measured. Any other quantity that can be specified in terms of this can be calculated. Speaking with numbers refers to general computations and calculations, and these include accuracy, which measures the closeness of agreement between a measured computed value and a true value, precision, which measures the closeness of a value obtained via multiple measurements and the true value, uncertainty, which estimates the error in a measurement, and also some others such as sensitivity, resolution, error, and confidence limits are considered. As mentioned before, some of the pedagogical strategies can be supported by computational virtual tools that enhance the students' understanding of the link between the mathematical theory and practical application of the course content. Several tools have been created in the past years with the aim of increasing the interest and engagement of students. Such tools are effective methods of learning as they enhance the student's understanding of the mathematical and physical concepts behind the theory, as well as the different applications in areas such as antennas, propagation, microwaves, radar, microelectronics, and so forth. Here are some examples of tools for assisting in teaching and learning electromagnetics. They can be categorized as either tutorial-based problem-solving resources or as simulation and visualization interactive tools. These tools have been developed in the MATLAB environment and they cover a range of electromagnetics topics. For example, on the left side of the slide is an antenna package for the visualization of radiation characteristics of planar arrays of isotropic radiators. The middle shows virtual time domain reflectometer tool for the detection and identification of faults along finite length transmission lines. This tool, for example, was developed using finite difference time domain derivation of the transmission line equations. The top image shows the main interface, while the bottom image shows snapshots of a plane wave propagating along the z direction in free space at different time instances. On the top right of the slide is a ray shooting package for the visualization of ray paths for ground wave propagation simulations. And finally, on the bottom right of the slide is a tool that simulates electromagnetic fields inside a parallel plate waveguide with perfectly electrical conducting bodies in 2 dimensions. These and more visualization tools are publicly available. You are all welcome to contact the authors if you would like to use any as a teaching resource for your courses. In this slide, a tutorial-based problem-solving tool that uses a randomized problem generator and a solver engine is presented. The tool includes an extensive list of problems from topics such as electrostatics, magnetostatics, dynamic fields, and transmission lines. The student attempts each of the random problems presented in the screen. In the event of an incorrect answer, a library of anticipated errors is used to provide feedback about the appropriate method to solve this type of problem. We call this smart error detection. In the event of a correct answer, a report is automatically issued to the user and the information is stored in a local database. The top right image shows a visualization of the electric field vectors between the 3-point charges. This visualization supports the background of the randomized problem. The tool was developed to be used in the Electromagnetic Fields and Propagating System course for second-year undergraduate students from the Bachelor in Electronic Engineering at Griffith University. The tool was provided to the students so they could practice problems in their own time and at their own pace with the assistance of the textbook. To evaluate the effectiveness of the tool, anonymous student feedback was collected through a survey, which is shown at the bottom right of the slide. Students found the tool useful, they described the tool as an alternative and fun way of learning, and a good tool for practicing problems for exams. This resource can be applied across the complete course and many other mathematically based courses. Electromagnetics education has been transformed in the past year. While the fundamental theory remains the same, there has been a proliferation of strategies for teaching and delivering courses. Blended learning strategies as well as online and hybrid delivery modes have been implemented to mitigate the challenges experienced by the global pandemic and have been retained to allow greater flexibility and active participation for students. However, it is important that in this increased complexity, electromagnetics educators retain the fundamental features of electromagnetics in their courses, regardless of the mode of teaching or techniques utilized. This is especially important to ensure a uniform and efficient context-independent learning and teaching practice. Thank you for your attention. This is the list of references used in this study. It includes from the 1990 reference to the current ones that allowed us to understand the current challenges and trends in electromagnetics education.